like to share. And lastly, we can have a metallic bond, and a metallic bond is where we have a C of valence electrons.
Not the letter C, and SEA, like the ocean.
Like the ocean. And basically what you've got here, pictorially, is you have you have a piece of metal. All right, and the piece of metal has, in the center of each atom, a nucleus.
Positive nucleus, yes.
A positive nucleus. So to help illustrate a metallic bond, Mr. Sams is holding up a...
Do you remember the baseball bat from last time?
Why isn't it not in my hand?
Yeah, because, you know...
I hit you over the head last time with it.
Vengeance and, you know, paybacks and stuff.
All right, so if we take a look at this aluminum baseball bat, it's held together. Yeah, there's lots of different metal atoms in the baseball bat. And so if you look at this particular thing, there are lots of little positive charges. And those positive charges, somehow this piece of metal is holding itself together since it is, well, since it's a metal.
It's together.
Yeah. So if we look back on the screen, think of this as the big piece of aluminum, and then we've got electrons. Now, one thing that's true about a metallic bond is, or about all metals, pardon me, is that the electrons are free to move around the atom.
That's why they're good conductors of electricity.
Yeah, you wouldn't want to stick the baseball bat in the electrical outlet. That would be a bad day.
I'd have a hard time doing that.
And so since these electrons are free to move, and they don't actually live with a particular atom, they are kind of, it's like a commune. They
delocalized.
Yeah, big fancy is they're delocalized, means they, what does that mean, delocalized, Mr. Sanders?
They are not in a particular locale.
And so if you kind of look at this chart here, the way it is, this area right here on the graph has a charge that's roughly negative, doesn't it? And since there's less electrons over here, this area over here is positive. And guess what? Positive things are attracted to negative things, and that's what holds it together. So just the random motion of the electrons causes that metal to stick together. Okay? Now let's talk briefly about a covalent bond and bond distance. This is really not that, this looks more complex than it actually is, and people get kind of confused by this. But basically, if you take... Actually, maybe we should do a diagram of a covalent. Well, they do have it here. They've got two hydrogen atoms, and then these little red dots here represent the possible locations of an electron. Remember we talked about the quantum mechanics things. And as you get them closer together, actually, if you think about it, that would cause them to want to repel because electrons have the same charge, and that would cause them to repel. But there's also an attraction of this electron for this positive nucleus. And so that's what is drawing this atom together, and this nucleus is attracted to, say, this electron. So as you draw them closer together, so if they're far apart, they're very separated out here, and then we come across on this graph closer and closer, you reach a point where they have the minimum amount of energy, which makes it the most stable situation.
And if you smush them too close together, the nuclei actually start to repel each other, so that's why it has some higher energy there.
Yeah, so it reverses here. Now, if you get the nucleus together, the positive parts too close together, then they will repel. And so it's really the attraction of one atom for the electrons of the other is really what's going on. And there's a particular ideal length that has minimum energy. This just happens to be the hydrogen atom, but if I had, say, H bonded to carbon, you would have a similar type of a graph. And you could figure out what that bond length is that way too. All right, that leads us to a concept called electronegativity. What's electronegativity?
It's how much something likes electrons, basically.
So the attraction of one atom for the electrons of another.
Yep. And as a side note, to have electronegativity value, you have to be participating in a bond. Okay, so you'll notice on this chart here, the noble gases are not listed. There is no value for the noble gases listed because, for the most part, they do not form chemical bonds. So we don't assign an electronegativity value to them.
Yes. So let's illustrate this with a little demonstration. What do you think?
Okay.
All right. So, Mr. Sams, I see you've got a ball.
I do. It's an electron.
And I have a ball.
Hey, look.
And you know what? I'm like that chlorine atom we talked about.
Yeah, and I could be...
my twin. The other chlorine.
The other chlorine.
And so I guess we need to...
share.
Do we share?
Yeah.
So we could share.
So, yeah, we could share the ball. And
but you're like my twin.
Yeah, so we both have it the same amount of time.
So the electrons are like shared right equally between us, right?
Yeah.
Oh, okay, cool.
Yeah.
Well, what if I was like... I was a fluorine atom.
Okay, and I'm hydrogen.
Oh, cool. Okay.
Little tiny hydrogen.
So if he's fluorine and I'm hydrogen, hey,
I'm hydrogen and you're fluorine.
I'm fluorine. That's right.
I'm hydrogen.
Okay, that's right.
Yeah.
I'm sorry. I'm fluorine because I'm stronger. You'll see. That's why I picked fluorine. So should we share?
Yeah,
Okay.
sure. Just form our bond.
Now we gotta like play
Yeah.
tug of war.
Yep.
And guess what, ladies and gentlemen?
Uh,
Because I am stronger! I win. The electrons are unequally shared because I am stronger than him. I'm not strong enough to take them, but I am strong enough to share them unequally because the electrons live closer to me.
Yeah.
I am
So he lured me in, like said, yeah, let's share the electrons, and then he's gonna hog them all the time.
I'm going to hog them all the time. So
Like
that's
when
the
the kid
idea.
down the street says, let's play, and then he won't let you play the ball very often. Yeah.
Ha! Gotcha. So back on the screen, guys. Hopefully you figured that out. The whole point here, of course, is that some are stronger than others. And of course, me being the fluorine atom, I am stronger. I have a strength of 4. That's the strongest of all the elements. Mr. Sam's was a mere 2.1. And so the electrons live closer to me than they do to Mr. Sam's. Let's illustrate that with a picture. So he was H, and I was F. He has 1 electron, and I had 7 electrons. If you don't remember how I got the 7, you'll learn in a little bit. And basically what happens is this is sort of picture 1. In picture 2, the H and the F, the electrons are shared, but if you look kind of the way I've drawn them, they definitely live, if this was the center line between the H and the F, they live closer to me than they do to him. And so therefore we could draw the bond as H, F, and we draw it just a single bond, but we'd actually would draw an arrow like this way and put a positive right here and say that the stronger one gets the arrow towards them. Now when we did the chlorine, when you draw the Lewis structure looks like this, and this is where they have the same value. So it was a 3 fighting with a 3, right? If this was a 3.0 and this was 3.0, they are like twins, and so it's an even Steven.
Yeah, I have twins.
Yeah, you have twins at your house.
But they're not identical.
But they're not identical. Yeah, and so in this case, the fluorine was a 4.0, and this was a 2.1, so 4 is stronger than 2.
And Lucy is stronger than Dorothy.
There you go. All right, now,
For now.
at least for now. Now, let's talk about the trend on electronegativity. As you go across, they get larger, so that makes fluorine a highest one, and as you go down, as you can see here on the sign here, they go decreasing. So the lowest one is francium, and the highest is fluorine. So that's how you can know that. And it's really because the fluorine wants the electrons the most, and it also comes back to the size. The size makes a big difference. And so it's got the positive charge. Since he's smaller and that nucleus is close, he's more attracted to the electrons, to the hydrogen. So if you ever ask that question, why, for electronegativity, you can answer it. Okay. You know, this isn't a very important one. Okay. That leads us to the concept of a bond polarity. And we've already alluded to this. We just haven't talked about it.
We haven't given it a name yet.
Given it a name. What we just saw was bond polarity. Actually, let's do polar bond. A polar bond, what is that?
It's when you have a covalent bond and the electrons are shared unequally, just like fluorine and hydrogen did.
Yeah. Unequal sharing of electrons. And then a dipole moment. A lot of people get this confused. On the AP test, they like to use this term for dipole moment. It is when you have a polar substance.
Yeah.
Now let's talk about polar. Well, we haven't got polar yet. Polar bond. Yeah, polar. What does that word polar mean?
Polar means it has an end or 2 ends.
It's got like a positive end and a negative end.
Yeah.
Now, one thing we didn't do. Let's go back a couple of slides. Since
It's like a polar bear has 2 ends, a front end and a back end.
there you go, something like that. Yeah, it does. Yeah, I'm not sure that's why they called it a polar bear.
Is that no what?
No, I think it's because it lives in the polar region of the world.
I get it.
Yeah, yeah. Now, the point here I wanted to get to is this fluorine, since the electrons are more on this side, and electrons have a negative charge, she has a slightly negative charge. I guess I'm the ugly one now, right?
Yep.
And this little symbol, by the way, means slightly.
Yeah.
And this end is slightly positive.
It's a lowercase delta.
Yeah.
Uppercase delta means change. Lowercase delta means kind of, sort of.
Yeah, so it's sort of negative and sort of positive, and that makes this, if you will, this little bond, a little magnet, where this side is negative and this side is positive, although it's slightly negative and slightly positive. Actually, positive and negative, I did it backwards, but you get the idea, I hope. All right, so a dipole moment is a polar bond.
Molecule.
Molecule, thank you.
Yeah, it's basically just saying that something has a plus end and a minus end.
Yeah, and a dipole just means you got 2 poles. Really, they're all kind of saying the same thing, but I want to make sure you understand that because in the AP test, sometimes they use different terms.
Yeah.
And so a polar bond has an equal sharing of electrons. And how do you know if you have a polar bond? Okay? How do you know if you have a polar bond? You have to have an electronegativity difference. You have to use this table here. And do I have any blank white space? Looks like I don't. So let's actually make a little chart here. If you have a electronegativity difference between 0 and 0.4, it's considered a nonpolar bond.
Yeah.
Because that's the chlorine. Because what's the difference between 3 and 3?
0.
0, so that's nonpolar. And then if it's between 0.4 and 2.1, it's considered a polar covalent. That's where there's unequal sharing. And if we did this one down here, 4 minus 2.1, I think it's at 1.9, isn't it? So that would be a polar covalent bond. And if you are higher than 2.1, any number, higher, greater than, this becomes ionic.
Right, it becomes so polar that there's a complete transfer of the electron is essentially what happens there.
The example we gave was in